Okay, so yes, I put it on a recording mode just now, so I hope everything be fine with this recording. Well, by the way, we just started, so I guess it's not a problem. So looks like when I start to borrow from the second place here, it's a not place of tens, like in a base 10, it's place of 4. So because we're in a base 4. So you don't borrow 10, you just borrow 4. And that 4 with 1 is actually 5, right? So 5 is what is sitting now on that position when you borrowed. You borrowed 1 4. Okay, so from 5 I can subtract 2 and get 3. And that looks like what they actually get in a base 4. And then I subtract 2 of those 4s and 1 4, and we get another 1 4 in a base 4. So it's not 13, we already know it's a 1 3 in the base 4. And that's exactly what we ended up with, and that's the answer for that example. So those people that are not sure and don't feel very comfortable with this basis, which I totally understand, could possibly write those numbers given in the base 4 as numbers in the base 10 and then subtract them. So if you have 3 1 in the base 4, then what you get is powers of 4, just like I did above. So it'll be 4 to the 1, and then also 4 to the power of 0. And analogously, with 1 2 in the base 4, we'll also have 4 to the 0 and 4 to the first power multiplied by those two given digits. So these be two numbers that they actually talk about. So here I have 3 times 4 or 12, right? With 1 that is 13. And for the second, I have 1 4 and a 2, which is 6. And when you subtract 13 and 6, that's what we definitely can do in a base 10, right? I get 7. And then I need to write that 7 in a base 10 using powers of 4. That looks like 7 could be treated as a 1 4 and remaining 3 1s, right? So we get this 7 as a 1 times 4 to the first power plus 3 of those 1s. And this is same as we just produced as 1 and 3 in the base 4. So 3 is here, right? 1 is here. And that's the one that we have here. So I'm not sure if that's more helpful because it looks like it's longer way of doing the problem. But if you are used to convert to base 10, then definitely this could be an alternative. But of course, just using this subtractions in the base 4 directly is probably the way to go. So as usual, I recommend to make a print screen of all that so you can better see the process. In fact, that's a solution that you can actually read that textbook is providing us with. So, and probably if you can follow through one of these examples, then the others will be pretty much the same. So let me go to the end of the section where the homework exercises were and see which ones you would like me to do from this additions or subtractions. So I can help you with those. If you have anything that you would like me to do for you today, please don't hesitate. If you tried something So sounds like 19. Let us do base 7 subtractions. So just to prepare numbers in a base 7, looks like the digits here correspond to powers of 0, 1, and 2 of 7, right? So the problem number 19. So we'll do 19 and then we'll do 23, of course. So looks like the numbers we have here are actually so many powers of 7. So for example, 5, 6, 3 in the base 7 is going to be 5 times 49, 7 squared, right? 6 times 7 to the first, and then 3 times 7 to the power of 0. So that's how I treat this. So when I look at the last digits, when I think of 3 and 4 that need to be subtracted, as usual, looks like I need to borrow. So borrowing 1, 7. So we'll be left only with 5 of those 7s. So I put 5 up here. And then when I bring that 7 to 3, I'll actually have 7 plus 3, which is 10. So this be the actual number that I have on that position. And I subtract 4 from it. Please notice that when I write it as 10, it's base 10 already. It's not going to be base 7, right? So when we subtract, yes, we use base 10 for subtraction. So 10 and 4, and this becomes 6. And now I move to the next place, because now we're subtract from 5 the 6, and looks like we're short in digits again, right? So what I'm going to do is borrow 1 up there, but that 1 will be not 100, but 49. So maybe I can just clean that 5. So it's staying. So get this. See, trying to fit it in this and kind of hard. So that was 10. But now I used to have 5, but 49 came to it, because when I borrow, it was from place of 7 squared. So with a 5 that I used to have on that position, now I deal with a number 54. See, 54. So that's what we actually have here right now. And from 54, I subtract 6 of those 7s. So from 54, I subtract 54, 6 of those 7s, which is actually 42, right? And see what we're going to get when we do this. So it looks like that would be something like digit 8. So this is probably not the best way to do it, because it looks like it's getting all kinds of complications. So that's why they don't recommend to treat it as 7 squared. They recommend to treat it as if we just started. So if that 5 was also like a last digit. See, when you get to this artificial systems of numeration, the one that we are looking at right now, please notice that it's probably never been used anywhere. And that's why we're trying to always convert it to 10. And that's why it's so inconvenient looking, right? So that's the reason why I once took care of this last digits and put 6. And let me put 5 in different color, because that way I think we better keep track of it. 5 is here. Then instead of, once again, thinking of 49 and then that 5, which is 54, I'd rather do subtraction not from 54, but just from 5 and borrowing 1 from the front digit. So leaving it as a 4. So here will be 4 for the first. Now that 5, let me do it in blue so we maybe better keep track of it. We'll get to add it with 7. And that's the whole point of story. So we actually subtracted from 12. So from 12, I'm going to subtract that 6, and 6 will be coming down. So again, I used to have not 6, but 5. Remember, I borrowed 1. And now I'm going to, since I'm short, because I subtracted 6 on the bottom, 5 minus 6 is not working. So I borrow 1 digit from front, but that'd be like a 1, 7, not 149. So that 7 that I borrowed needs to be added with 5. That's what I just did here. And it's 12. So I subtract not from 5, but from 12. That number is 6, and that's how I get 6. And then we finish with this exercise. Looks like the first digit, which is 4, and 1 nicely subtractable, and that's 3. So usually when you deal with this subtractions, first digits are always fine, but we got 3, 6, and 6 in a base 7 here. So also there was a question about number 12. Well, I'll do it in the next step. Let me do 23 first. So it looks like we now deal with base 3. Please notice that analogously to problem number 19, where I had base 7, so allowed digits were up to 6. So if base is 7, then there is also 0, and we have all digits up to 6. Here in the base 3, the allowed digits are only 1 and 2, as well as 0. So there'll be 3 digits. And now I'm going to start borrowing and see how this all could be done. So I borrow from, looks like, number that will be treated as powers of 3. So there'll be, I guess, 3 cubed, which is 27. That's on the first position. Next position is 3 squared. That's where I'm going to borrow from, and that'd be 9, right? And then I also get first power of 3, which is just a 3. And then 0 power, which is 1s. So it looks like I don't have enough 1s. So I should have borrowed from the upper one, but upper one doesn't have enough. So I borrow all the way here from 2. So this way, I no longer have 2, but 1. So what I did, I just borrowed 1 digit here, which is actually 3 squared. But I don't need this entire 3 squared in there. I just need to get a part which is going to be good enough for me to subtract. And the part that is good enough for me to subtract will be, looks like we have here 0, and I need to subtract 2. So I need to have plenty of 1s. So what I do is I get to borrow this 3 1s. In other words, there'll be a 3 here that I borrowed, right? And since I actually went to the position that deals with 9, so I borrowed actually 1 9, then if I utilize 3 1s, then there will still be 2 of 3s left. In other words, the 9 I borrowed, I write as a 2 and 3, and that 3 deals with 1s, powers of 0, and 2 deals with 9s, which is powers of 3 squared. see how this works. So if you, oh, 3 to the first, sorry, 0 times first. So I have 6 and 3 that I split my 9 with. So there'll be 2 3s here and 3 1s. So that's why I recommend to probably turn these numbers into base 10, and you'll be much nicer subtracting those, because I think for this exercise is a little bit way too involved with all these conversions. Well, anyways, now we can actually go ahead and nicely subtract everything. And that's the point. So 3 minus 2 is 1. 2 minus 1 will be 1, because all these digits are allowed in that system. 1 minus 0 is 1. And then you subtract in 2 ones, and that's all you need. And you produce the number in the base 3 for the answer. I know it's something that probably one needs to think through once again, but if you don't want to, I totally understand you. You could just write 1200. Look at that. So it may be a little longer, but it's more straightforward, I think, because you will be dealing with more familiar process. So it's 3 to the 0. Here's 3 to the first. And so forth, so 3 squared and 3 cubed, right? So the actual numbers that we subtract will be here. The first is 27 with 9 times 2, 18, and with zeros. So you actually have 27 and 18, which is 45, right? So that's the first number. And a base 10. So that's the one here, base 10, 45. And the second number, analogously, I could treat as a put digits 1, 0, 1, 2, right? 1, 2. And with the attached powers of 3, so it's 3 cubed and 3 squared and so forth. So it looks like this procedure is the same for all problems, and maybe you will prefer to do it like that. So the reason I'm showing it both ways is for some people that do homework decide to convert to base 10 if that feels more convenient. So here's 27, this is 0, this is, because times 0, right? This is just 3, and the last is 2. So when I add these, I get altogether number 32. And when you subtract in the base 10, 32 and 45, the result will be 13. 13, right? And then you write this 13 in the base 3 like that, so you can check this out, of course. So when you put 13 with powers of 3, so it looks like it'll be 3 squared, so there is a 9 in it. And then you get 1 3 to the first, right? Which is just a 3. And the remaining number 1, which is 1. So let me put these digits here. So 1 3 squared, 1 3, and 1 just digit 1. So when you have these all put together, so you get 9 and 3 and 1. That's indeed going to be 13, but we write this first digit, so I put them also in black. So it's 1 3 squared and 1 3 to the first and 1 3 to 0. So there are 3 ones in a base 3. So if this is better looking, then again, you can go ahead and use that. If you find with that subtraction, that's the other alternative. But I know it is quite tedious, so it is a good idea to try to think of it, and we can always go over this again on Friday if it's unclear, because as I said, it's definitely different with all you encountered before. And please notice we kind of heavily use base 10 to do all this subtraction. So we don't really subtract in the base 3, we subtract in the base 10 because we used to base 10. And that's, I guess, another holdup of the process. So 12, addition for a change, and it's in the base 16. So digits in the base 16 are 0, 1, dot, 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 through 9. Those are ones we use on daily basis. Then we have more digits. There should be 16 of them. So such digit as A will go for 10, B is 11, C is 12, D is 13, E is 14, F is 15. So whenever you have base, let's say 3, digits are 0, 1, 2. So 3 is never present because 3 is already playing the role of tens. Same here. So if you have base 16, then you have 15 different digits and a 0 on the top. So that's how we get 16 different digits. So A stands for 10, B stands for 11, C for 12, and etc. This is 13, 14, and 15. So the reason I'm doing it is because I want to know what numbers we actually have here, because you see letter B present. So B is actually playing the role of 11 in a base 10 system. And when I subtract from 11 number 4, well, I get some digit that is present in base 16, because 11 minus 4 is 7, right? And move to the previous position. Oh, sorry, I'm not subtracting, I'm adding here. I should be careful. I'm adding here, so it's not 7. I'm gonna put 11 plus 4, not 11 minus 4. There is a plus sign. Okay, so we can actually switch this to something else. So I add 11 and 4, and what I get is 15, right? And what is 15 in that base? Do we have such a digit? And yes, we do. It's F. Again, 11, that's B, plus 4 is going to be 15, and that's digit F in the base 16. So we have that digit. Isn't that just amazing? And then I move to the next column and add 3 and 9, which is 12. And notice that 12 is also present in the base 16 at C. Isn't that interesting? C is here. And finally, I add the first ones, it's 5 and 6, and 5 and 6 will give me 11, and it's also present here. So it's going to be something like that in a base 16. So I didn't really need to convert anything because those digits were large enough. I would probably convert if they had like A with B added, so it would be like 21. So then I would need to pull out 16 and carry something over. But I guess they didn't really get that far. So looks like in the base 16, it's not that bad to add. But you still need to know those extra digits. Okay, so let me clean all that. So if you can take a print screen to clean, because now I want to multiply something for you. So the print screen, I'm gonna stop share. Well, it's still being the recording, I hope. Oh, by the way, I just looked at emails and noticed that somebody wasn't able to open my previous lecture. Somebody else could not open the previous lecture, or he didn't try. Oh, so you could open it, huh? It says expired. Interesting. Let me try to open it because that's interesting. How long this lecture actually stands. Maybe they just hold it for a very short time. Let me see here. So it should be somewhere. Let's see. I need to find oh, here it is. So there is a passcode. So it looks like there's pretty crazy passcode they put here, but Zoom creates it. So let me try to click on it. The record doesn't exist. Ah, so we actually need to watch this record today then. I see, that's how they said it. See, our college, I think, didn't buy a large mailbox for the Zoom, and that's what causes it. So they do have these recordings, but they exist only for one day. So if you don't watch the lecture the same day at night or something, then it expires. I see. Well, I guess there is not much I can do, so I will be sending you this recording today in the morning. And if you want to watch it, then try to do it up to tonight, because tomorrow it may not be possible. And I think the main reason is that when they purchase this program, they also purchase some storage space from Zoom, so they need to, I guess, expand the storage space, and that way these lectures will stay there for a longer than a day. I will be talking with our computer genius people today on campus, and I'll see what can be done. Maybe they'll help me with some settings on the computer. So by Friday, I hope we could expand this a little bit, but again, I'm not sure, because if the college didn't pay for that expansion, it may not be possible. But again, I know from experience, I worked in some other college, and then they had to buy a little bit more of memory to hold all these lectures. But anyways, let me work on this. Thank you for letting me know, because sometimes things could be fixed, but sometimes could not. So anyways, we're here in the base 6 right now, and we're gonna try to multiply these numbers. Again, if you turn them both to the base 10 and then multiply and then convert back to base 6, it'd be pretty standard procedure. So that way you wouldn't care whether you multiply or do something else. But let us just follow through. How can we possibly multiply these two numbers still in the base 6? So if I go 2 times 4, it's 8, but I cannot put 8 in the base 6, because in the base 6 we have only digits 1 through 5, right? So if I produce 8, then I need to turn this into, so base 6, those are powers of 6. So it looks like it's going to look like 1 6 plus 2 1s, right? So it's going to look like 1 2 in the base 6, number 8 in the base 10. And then I just put 2 down, and I carry 1, because it's 1 6, so it goes to place of 6s. And then I multiply again 2 by 3, so just like we used to, and that'd be 6, but I need to add 1, and that's going to be 7. So now I need to write down that 7 in the base 6. So what I have is first power of 6 and 0 power of 6, which is 1. And they will be just added way they are. So it'll be 1 6 and 1 1. 6 plus 1 is 7. So this number is going to look like 2 1s in the base 6. So I put those 2 1s, and that's all in the base 6. So it looks like that's what they produced here eventually. So you can actually see this nice little explanation they have. So let me do one from that section at the end. And so I'm gonna go to this homework story and multiply some number. Notice they don't have many examples because I guess these multiplications, well, I don't think you encounter them too often, but I don't think you encounter this too often at all. So let me try to base 6 again, since we just did the exercise, and maybe that'd be a little bit more convenient. So 32 I see is done in the base 6. So let us multiply. 5 by 3 is going to be 15. So now I need to write this 15 in a base 6. So if I try 6 to the first and 6 to the power of 0, that'd be enough because 6 to the first is 6, but 6 squared is already 36. So that exceeds the number we have. So it looks like it'd be 2-digit number. So it looks like it'd be 2 times of 6s, so it'll be 12. And remaining part should be 3, so that's going to look like 3 ones, right? So the number I produce is 2, 3, base 6. And as usual, we just write last digit, which is 3, here. And carry 2 for the next position. And we multiply again. So 5 and 4, which is 20, and we actually ended up with 22. 22. Please notice that again, it didn't exceed 6 squared, which is 36. So we're still good with only 2 digits. And 22. So to get closer with 6s to it, I need to take 3 6s because that's going to be 18, right? And then remaining from 18, I'm going to have 4 ones. 4 ones. So the number is going to look like 3, 4 in a base 6. And again, I just put down last digit, which is 4, as usual, and carry 3 here for the first position. And multiply the last digits. So the one I just produced, 3 by 5 and get 15. Oh, actually, sorry, 5 by 5. 5 that sits here. It's 25 and 3 is 28. So the next number I produced is 28. 28. And then this 28 needs to be, again, written as with powers of 6. So it looks like we have 6 times what? 5 is too much, it's 30. So 6 times 4, right? Which is going to give us 24. And the remaining from 24, there will still be 4 ones. 4 ones. So these digits, 4 and 4, is what I have for presentation of 28 in the base 6. So I put them down, 4 and 4. I know it is different with all you see around yourself, but that's multiplication. I think I'm not going to go over division because once again, if you really want to divide, then you can just turn these numbers to base 10, divide, and then get the result. And here, please also notice that you might get some remainders that is not very pleasant thing. So if somebody wants, you can still try, but I don't think I'm gonna spend time on this. There's just probably one exercise that you could try for homework. So I would say just concentrate on addition and subtraction instead of this. I wanted to introduce you with multiplication, but in some cases it could be a little bit way too challenging. So anyways, there is one more section of this chapter that I just want to say a couple of words about, because that's the section that could be useful for some people that might travel in various places, like, for example, China. I know if you've ever been to China, you might probably noticed, if you've been there, that there are no numbers on the houses if you're trying to find some address, you won't be able to see the numerals that you used to, because in China, there are different numerals, not just the letters, but there are also different digits. So notice that if in China, you're trying to find the house, let's say numbered 333, then it's going to look like that. So the 1 3 is going to look like that. The other 3 is going to look like that. And the third 3 is going to look like that. We say, oh, well, that's not hard. It's 333. Well, maybe 555 will be a little bit more challenging, right? Or if you get 575 or 574 in Chinese system. So if you actually do go to China, then you're gonna have this thing. So 5 is gonna be something like that. Like this, and like that. Then 7, it will be this thing. It's like a T. Although a person from China will say your T looks like my 7, not my 7 looks like your T, but whatever. So, and then 4 finally is going to look like that. So if you will look for the address 574, and I actually experienced that you're not going to find this digits that you used to. You're going to need to look for this. So probably better get a taxi and go. But so that's what they're talking about here. Of course, I'm not going to make you memorize those things, so somebody may never need that. But I think knowledge of such a fact could be, who knows, useful if you go especially to rural China's places where people don't speak English, and you're going to need something, and that'd be quite difficult to even purchase because you won't know what these digits are. So if you ask for the price, they'll write something for you in Chinese digits, and well, I guess it'd be quite difficult. So messages, well, you can get prepared. So the little table like this could be definitely helpful. But my goal for today is just to give you a little bit of introduction to this, and I'm not going to be testing you on this section because I don't expect you to memorize this traditional Chinese numerals. They actually in the big cities put regular numerals on this, like big streets, but if you go away from big street, you will definitely experience tradition. So anyways, there is another system that we encounter every once in a while. That's Roman numerals. We don't encounter with all of them. So let me clear what I have here. So stop sharing and then share my screen once again. So we encounter Roman numerals, right? And we know a few of those. So we know how to write 1, we know how to write 5. Probably some people know how to write 10. Well, it turns out there are numerals for 50 and then 100 and for 500 and for 1,000. So these are letters that they use for Roman numerals. And here's a table of conversion. So you can always convert to Roman numeral if you feel like it. Notice it's dealing like base 5 or something numbers, but not really. So it's still base 10, fine. But they have presentation for 5, 50, and 500 in them. So those are ones you are familiar with, and sometimes, rarely, but sometimes they put big numbers in Roman numerals. And the system that you probably don't encounter because it's not been in use, they say, for a couple of thousand years, that's Egyptian numeration system. And it's also base 10. So here's the table of conversion, where I think maybe in the previous page, of those digits to base 10. Yeah, here they are. So you can see that if, for example, you try to write number 9, then all you have to do is put 9 this 3 more and 3 more. So in Egyptian system, it will be just 9 of these bars. And if you if you go all the way to 100, so let's say if you go 90, then you need to put 9 of this, they say heel bones, and so forth. So it's not very convenient that because the numbers get pretty long, right? Like here, they say, if you're trying to write some big number, you can actually read it. So 100, how many hundreds, how many spirals? 1, 2, 3, 4, 5, 6, 7. So that's 700. Then 1, 2, 3, 4, 5, 6. So 764. So this is the number 764. It looks like you need a long piece of paper to produce big numbers. Let's say if you're like Bill Gates and trying to write down how much you left on your checking account, then you're probably going to need an Egyptian system. You have extended paper to fit all that, because there'll be also some thousands, there's some 10,000, some hundreds. So you can imagine how long the number is going to be. It's probably going to be page long. So this is going up to 1 million. So they're not prepared for billions though. So, and that's going to take a lot. So this million is already big numbers. You say, oh, wow. So you raise your hands up in there. But I think if to write billion, you need to write what? 1,000 of this million. So it'll take you probably a long time to write just 1 billion. But if you want to go to trillion, that's going to take you probably a year. So it's not convenient system. So it looks like Egyptian system is not dealing with big numbers. It's pretty simple in a way. Also, it seemed to be quite artificial. So there should have a little bit bigger symbols for bigger numbers. So anyway, so these are the systems of enumeration that we actually do encounter in the real life, possibly. Well, I guess not Egyptian, but the Roman numerals and Chinese digits. So it's good to be aware of those. I'm not going to test you on this. As I said, you could read that little section if you feel like it, but you could also skip it. You could also skip it. So today I wanted to give you a little quiz and have you try to add a couple of numbers, maybe in a base tool, just for fun, because we haven't had a quiz last time. So maybe I can just do one in a base tool, like exercise 4, and then have you try another one. So if I'm looking at the base 2, the numbers we have here to add, we have last digits ones. So when I add 2 ones, it's going to be 2, but 2 in a base 2 is going to be 1, 0, right? Why is that? Well, you could write this as a 1, 2. So it'll be 2 to the first power and 2 to the 0 power, place of 2's and place of 1's. So it's 1, 2, and 0, 1's. That's what 2 is, right? So since it's 1, 0 in the base 2, I put 0 here and carry 1. And guess what I get when I keep adding again? 1 and 1, I get again 2. So again, I have to write it as 1, 0. So I put another 0 and I carry 1. And again, I add 1 and 1 and I get 2. So looks like I need to write it as 1 and 0. So I put down 0. And I have to carry 1, but there is nothing to add to it. So I just put 1. So in the base 2, this is going to look like 1 and 3 zeros. So you could use analogy and try to do exercise 3 for today's quiz. Notice you'll be adding 2 ones and producing 2's anyway. So looks like it'd be the same idea as I just went through in exercise 4. So let me stop this recording for today, and I'll let you